We all know pi, right? That number with endless, never repeating digits. We have seen the contest to memorize it. We have heard about supercomputers calculating it to trillions of places in a quest that never seems to end. It's the ultimate symbol of mathematical mystery. But what if I told you that all of that is completely pointless? What if I told you that for any practical reason you could possibly imagine, even the most extreme universe spanning calculations, the number of pi digits you actually need is shockingly small? Forget trillions, forget millions, don't even think about thousands. Today, we are going to reveal the exact number of digits NASA uses to launch and guide its spacecraft across billions of miles of empty space. And then, we are going to go even bigger. We'll find out precisely how many digits it would take to measure the circumference of the entire observable universe down to a width of a single atom. The answer is going to change you the way you think about pi, precision, and reality itself. For thousands of years, humanity has been obsessed with this strange irrational number. Pi, the simple ratio of a circle's circumference to its diameter, is so simple in its definition, yet infinitely complex. The quest to tame it is a story woven through all of human history. Ancient Babylonians and Egyptians had their rough guesses. The great Archimedes of Syracuse painstakingly pinned it down to a remarkably accurate range using his method of polygons. For centuries, that was as good as it got. Mathematicians from China, India to Persia dedicated their lives to tacking on just few more digits. In the 15th century, the Persian astronomer Jamshid al-Kashi calculated pi to 17 digits, a level of precision that, as we are about to see, was already enough for almost anything. But the chase didn't stop. With the invention of calculus, powerful new formulas let people calculate hundreds of digits by hand, a massive error-prone job. Then computer arrived on the scene. In 1949, the ENIAC computer calculated over 2,000 digits in just 70 hours, blasting past centuries of human effort in a single weekend. And from there, it became an arms race. Thousands of digits became millions, then billions, and today, supercomputers have pushed the record past 100 trillion digits. This relentless chase has baked a powerful idea into our heads. The more digits of pi equals more accuracy, and that more accuracy is always better. We just assume that somewhere, for some profound reason, all this precision must be essential. We built a cult around the infinity of pi. But the whole time, we have been missing the real astonishing truth. The problem with this obsession is that it confuses the perfect abstract world of pure mathematics with a messy concrete physical world we actually live in. In math, pi is a perfect concept. Its digits do go on forever without a pattern, and that is a beautiful fundamental truth. But in this physical world, nothing is perfect. You can't draw a perfect circle, you can't measure a perfect distance. Every single thing we build or launch is limited by constraints of reality. At a certain point, adding more digits of pi doesn't refine your measurement of real world. It just refines your measurement of purely imaginary perfect circle that doesn't exist. So the real question, one that scientists and engineers have to ask, isn't how many digits of pi are there, but rather how many digits of pi do we actually need to get the job done. And this is where the story takes a sharp turn, and this is where we leave the world of infinite ideas and enter a world of practical, mind-blowing applications. The real shock isn't how many digits of pi are there, but how few you need to encompass the entire cosmos. Let's start with something you see every day, the tire on a car. To manufacture a tire with a diameter of 2 feet, how many digits of pi do you need? If you use the classic 3.14 you learned in the school, your calculator circumference will be off by less than a tenth of an inch. For a tire, that's already pretty good. If you add two more digits, 3.1416, your error shrinks to less than a thickness of a human hair. So basically, any engineering on Earth, a handful of digits is more than enough. But let's go bigger, much bigger. Let's calculate the circumference of entire planet Earth. The radius of planet Earth is 6,371 kilometers. Let's say we want to measure its circumference with a ridiculous level of precision, down to a single nanometer. How many digits do we need now? Still not many. Using just 16 digits of pi would give you an answer with an error 30,000 smaller than human hair. Alright, you might be thinking, but that's just Earth. What about the actual rocket scientist? The people whose job is to slingshot a billion-dollar probe across the solar system and hit a specific target years later? What does NASA use? For their most critical and high-precision calculation for interplanetary navigation, NASA's Jet Propulsion Laboratory uses 3.141592653589793. That's it, 15 decimal places, 16 in total. Mark Raymond, chief engineer at JPL, put this into stunning perspective. Think about Voyager 1 spacecraft, the most distant object humanity has ever made. That's over 15 miles away. Now imagine a giant circle with a radius stretching from Sun all the way to Voyager 1. The circumference of that circle is mind-boggling 78 miles. If you calculated that massive circumference using NASA's 16-digit version of pi, how far off would you be from true answer that requires infinite pi? The answer would be just 1.5 inches. Let that sink in. Across a circle that spans our entire solar system, the error from not using trillions of digits is less than the length of your little finger. Any more digits would be completely washed out by other uncertainties, like the exact thrust of an engine, the gravitational pull of a passing asteroid, the limit of our own instruments. For navigating the solar system, 16 digits of pi isn't just enough, it's already overkill. But why stop at solar system? Let's put this to absolute mind-bending conclusion. Let's design the most ambitious measurement possible we can think of. We are going to calculate the circumference of the entire observable universe. First, our circle, the observable universe, the bubble of reality from which light has had enough time to reach us, has a radius of about 46.5 billion light years. That's a distance so vast, it's basically incomprehensible. Next, our accuracy. Let's pick the smallest meaningful unit of length. Let's choose the diameter of a single hydrogen atom. We're going to measure the circle that's nearly 300 billion light years around, and we demand that our calculations be accurate within the width of a single atom. This is the ultimate test of pi. To pull off this impossible sounding feat of precision, how many digits of pi do we need? Trillions? Billions? The answer is 39. That's all. With just 39 digits of pi, you can take the radius of observable universe and calculate its circumference to a precision smaller than a hydrogen atom. This is the aha moment. Think about it. For decades, our supercomputers have been churning away, generating streams of digits so long that it would fill every book on Earth 1,000 times over. And yet, for the most precise, most expansive calculation physically possible, we only need first 39 digits. Every single digit after that, the 40th, the millionth, the trillionth, describes a level of precision that is smaller than the smallest meaningful object in the cosmos. From physicist point of view, they are completely and utterly irrelevant. So why this number is so surprisingly small? It comes down to a simple but powerful principle, diminishing returns. Now think of it like this. The first digit of pi, the 3, gets you in the right ballpark. The next digit, decimal 1, refines your estimate by a factor of 10. The next, decimal 04, refines it by another factor of 10. Every decimal place you add makes your circle 10 times more perfect. But the impact of that refinement shrinks exponentially. What this really means is that even when your circle gets astronomically large, like the radius of the universe, you can make the error astronomically small without needing crazy number of digits. The math itself tames those huge numbers. Each digit we add gives us such a phenomenal boost in precision that we quickly reach to a point where any more accuracy is smaller than anything we can physically measure. In fact, if you wanted to go even further and measure the universe to a Planck length, the theoretical smallest possible unit of distance in all of physics, it would only require about 65 decimal places of pi. If learning that you can measure the entire universe with just 39 digits of pi has changed your perspective, consider subscribing for more videos that bust the myths of math and science. This channel is all about finding those shocking truths that hide in plain sight. And let us know in the comments what another scientific fact that you have always wondered about. We might just tackle it in a future video. So what's the point of calculating pi to trillions of digits? For physicists, astronomers and engineers, there really is no point. But for mathematicians and computer scientists, the chase isn't about practical applications. It's about pushing the limits of computation, testing the efficiency of new algorithm, and searching the pattern in a true mathematical randomness. It's the ultimate stress test for supercomputers. Pi, the number, is infinite, but pi, the tool for describing our universe, is finite. We don't need endless number to measure our reality. because our reality itself is not endlessly precise. It's a world of atoms and planets and galaxies, not of perfect abstract forms. And in this universe, you only need just enough pi to get the job done. Thanks for watching.